Hello and welcome. In this video we are going to look at thermochemistry. We want to see how different reactions tend to evolve in terms of energy. So what is thermochemistry? Basically thermo comes from the word heat, thermo, while chemistry we are going to be dealing with chemical reactions. So thermochemistry we are going to be dealing with how energy changes whenever we have certain chemical reactions taking place. So we are going to see that during certain chemical reactions, energy will be absorbed whenever we're breaking bonds, and energy is given out whenever bonds are being formed. So how can we kind of appreciate this concept that whenever energy is absorbed, we are breaking bonds, or the other way around, that whenever we're breaking bonds, energy is being absorbed? So let's take a look at water. We know that ice in this format, water is H2O, but we know that when ice is being formed, we tend to have what we call hydrogen bonding. So the dots you are seeing are kind of representing hydrogen bonding. So this is our hydrogen bonding. So we all know that whenever ice is melting to our water or liquid form, let's write water, we have a constant temperature. That is to say, during change of state, temperature remains constant. But the question is why? So during change of state, the energy that we normally apply to the ice, that energy, instead of being taken into to increase the motion of the vibration of these molecules of water, we shall see that energy being used to break the bond. That's why we tend to see the energy remaining constant, because the heat energy that we apply to the ice, instead of increasing the vibration of these molecules, we shall see it being used to break the bond. And as such, temperature will not increase because we don't have any increase in the kinetic energy. So what happens is that whenever we're breaking a bond, for example, this is the hydrogen bond in water or in ice, energy will be taken in. That is to say, energy is absorbed. So whenever a bond is being broken, energy is absorbed. However, when you look at a scenario where our water or steam, let's look at water. Whenever water is turning into ice, it's true still we have a constant temperature. However, now the water molecules tend to have more kinetic energy than the ice. But now for that kinetic energy to be reduced, we must have a decrease in energy, so that these water molecules can then be able to obtain a structure similar to that of ice. So we have to lose some energy so that ice is formed, so that the hydrogen bonds can now be reformed. So we shall see that whenever we tend to be forming these bonds, in the process of forming back the ice, energy has to be given out. That's why our water must become cooler, so that energy is given out as these bonds will now become prominent, the hydrogen bonding. So in summary, whenever we are breaking bonds, energy will be absorbed, but whenever we are forming bonds, energy will be given out. We shall be able to understand this concept better as we proceed in this course, so try to keep around. But for the meantime, that's some good introduction to thermochemistry. So we have different types of chemical reactions. We have those that will depend on whether heat is gained or heat is lost. So the first one is known as the endothermic reactions. Endo means within. Endo means within. If something is taken within, that means it is endo, inside. So these reactions proceed with absorption of heat from the surrounding. If you have your container and then you have maybe your mixture inside here. If you add the second reactant to this substance, if at all maybe we have a substance A and we are adding it into this other substance, let us call it B. If we notice a decrease in temperature when A and B are mixed, if we have a decrease in temperature, such a reaction is considered to be endothermic. Endo meaning the heat energy is being absorbed from the environment. Energy will be removed from the environment, and we shall have a cooler solution being formed when A reacts with B. We shall look at some different values. So in this case, it is usually denoted by a positive enthalpy change. We shall see what we mean by enthalpy change. But in this case, the temperature will always go down and will become a bit cold. So products are usually at higher energy than the reactants. It's a bit challenging if we say that energy is absorbed but the temperature is lowering, but we shall try to come up with a solution to that challenge. But during endothermic reactions, heat energy is absorbed from the surrounding, and then the solution tends to be, or the mixture tends to become a bit cooler. So how do we present endothermic reactions on an energy level diagram? On the y-axis we have our potential energy, or basically our energy in kilojoules per moles. So on the horizontal we have the reaction coordinate, meaning our reaction starts from here and proceeds to this side. So at this point here we have the reactants. At the start of the reaction we have the reactants. It could be A and B reacting. If at all we have a reaction where we have A and B reacting to produce C and D. So A and B are our reactants while C and D are the products. So at the start of the reaction we have the reactants. So this is our reference line. This can be our reference line, but we shall see that our reactants have an enthalpy of H1. This H1 is representing the enthalpy or the energy. Let's stick to energy for now because we haven't looked at enthalpy. So reactants have energy H1. However, as the reaction proceeds, we tend to see an increase in the energy until this point where then the energy will tend to move downwards. So this increase in energy here can only take place if something is done with A and B. For A and B to react, something must be done to overcome this energy barrier. So from here up to here. So this energy here is the activation energy. So EAT is our activation energy. So this is the energy that the reactants must be supplied with so that this reaction can proceed, because the reactants will not react on their own unless this barrier has been overcome. So at this point we usually have the activated complex, a complex kind of mixture between the reactants and products. Usually this activated complex is unstable. It may be containing radicals, may be containing ions, but usually it's unstable and it will have to break down to form our products. So here we shall have our products C plus D. So the difference between the energy level of the reactants and that of the products is what we shall call the enthalpy change. So this will be our enthalpy change as denoted by this delta H, which is positive. So it is positive because the products C and D they are at a higher level compared to the reactants A and B. When you look at H1, the energy of the reactants, and H2, the energy of our products, we shall see that if we are to get H2, the energy of the products, minus H1, we shall get our delta H. But because our energy of the products H2 is higher than that of the reactants, we shall get a positive value. That's why we always say that the energy of enthalpy change of endothermic reactions is always a positive enthalpy, because we always have products that are at a higher energy level compared to our reactants. So this is briefly about the energy level of endothermic reactions. So for the backward reaction, if at all we want to convert CD back to AB, we shall have to overcome this new energy barrier. So this will be the activation energy in this case. So briefly, this is some good introduction to energy level diagrams. We always have the vertical scale talking about the energy. So for endothermic reactions, the energy of the products is always higher than the energy of the reactants, and that means our products are less stable compared to the reactants because they have more energy. Usually things that have more energy are less stable compared to those that have less energy. So here are some examples of endothermic reactions. Photosynthesis, this is quite complex in terms of maybe finding or confirming that the reaction is endothermic, but at least we can use things like the we can use things like Hess's law to try and come up with the energy changes of such reactions. But we shall look at Hess's law as we proceed. Then we have dissolution of ammonium nitrate in water. So when you add your ammonium nitrate in water, if we have our ammonium nitrate and then we add it in water, we shall find that our solution will become a bit cooler. So we shall form our ammonium nitrate solution. So this will be accompanied by a decrease in temperature, and in that case our enthalpy will be positive. The same applies to change of state, although someone might assume that these are basically physical changes, but it's true. You can have a change of state in which vaporization and melting. For example, if you have a liquid, which is our water, vaporization and melting. When you look at melting, we are changing from solid to liquid. So if we have our maybe liquid in terms of vaporization going to gaseous state, so we shall go to our steam. So such reactions, we must apply, heat must be added into this system. But at this point we are looking at the point at which our liquid is turning into a gas. Yes, someone might feel the water is hotter, but it's not the reason as to why we might say it's endothermic, but the conversion of water molecule to our gaseous state is a bit endothermic. Heat must be absorbed by the water molecules, so the reaction is basically endothermic. So we also have exothermic reactions. Exo meaning outside. So such reactions will be well known by the release of heat, evolution of heat. Usually heat is given out to the surrounding. So it will be denoted by a negative enthalpy change. For endothermic, we had seen that it's denoted by a positive enthalpy. We shall see what enthalpy means, but for exothermic, we shall always get used that it's a negative enthalpy change. We shall see that now products will be at a lower energy level than reactants. So substances usually have a specific energy. So in this case, we shall have our energy diagram. We have the energy in kilojoules per mole on our vertical scale, and we have the reaction coordinate. So at the start, we shall have our initial reactants. We shall stick with A plus B, while we shall also have our products C plus D. So at this point, we shall have our activation energy, this one here, from here up to this point where we have the reactants. So this is the energy that we need to apply for A and B to react. So this is the activation energy. However, once this activated complex position is reached, it will then gradually or spontaneously go into the product direction. So one thing to note about the exothermic reaction is that the energy of the products C and D is below that of the reactants. If you look at our reactants, H1, it's higher than H2. So what does that mean? It means that our enthalpy change, delta means enthalpy change, our enthalpy change being equal to the enthalpy of the products, which is H2, minus H1. So remember, when you look at this energy diagram, as we move down, we are moving towards less energy, as you can see by the arrow. So that means H2 is lower than H1. So if H2 is lower than H1 and we are subtracting, it means the answer we shall get must be negative. That's why we shall say that enthalpy changes for exothermic reactions are always negative. However, for these exothermic reactions, we know that we shall always see evolution of heat, and that means we shall always see an increase in the temperature of the thermometer if at all we are measuring. So let's have a look at some examples of exothermic reactions. Probably we shall get some idea on what they look like. So we have dissolving sulfuric acid in water. You might have heard that never add water to the acid. In this case, we are trying to dissolve sulfuric acid in water, but this reaction is exothermic. If you get a beaker in which we have some water and then pour in our sulfuric acid, add a little sulfuric acid, and then maybe you can try to touch the walls of this beaker with your hands, you'll find that actually you shall have something warm being formed. You will feel the heat being evolved. So evolution of heat. Evolution of heat. So what does that mean? It means that if you had your thermometer dipped in this solution, you could see a temperature rise, because when sulfuric acid is dissolved in water, we have evolution of heat. So once the products release heat in their formation, that's why they will have lower energy. And if substances have lower energy, they will always be more stable compared to the initial counterparts, which are the reactants. Then secondly, we have combustion, burning of a given substance in oxygen. For example, if you burn graphite, which is carbon, in oxygen, it usually burns with evolution of heat. But remember, carbon will not easily burn unless you provide the activation energy, some little heat to it, so that the carbon can start reacting with the oxygen. So with evolution of heat. So the loss of this heat will cause the products to have less energy compared to that of the reactants. So lastly, change of state, freezing and condensation. Just like before, during freezing, molecules must lose energy. Water molecules, for example, in liquid form, must lose energy so that they can be converted into water molecules in solid form, which are just vibrating around a fixed position. So for this to happen, there must be loss of heat. That's why you will see that for you to turn water into ice, you have to kind of cool your water first. So basically, these are some of the common examples of exothermic reactions. Heat being given out. Yes, thanks for watching. In our next video, we shall try and look at enthalpy. I've been somehow unknowingly or without conscious trying to talk about enthalpy, but in our next video we shall try and look at it. Don't forget to subscribe. Let me know in the comment section below what you have not understood or what you would like me to throw more light on. Thanks for watching. Be safe.